Hey guys, so today what we're going to be talking about is techniques for evaluating limits. So last time we met, we talked about what are limits and how can we use a calculator to evaluate them. So today we're going to talk about what is the situation when we don't have a calculator, how can we still evaluate limits that initially don't exist. All right, so we're going to go ahead and start off with example letter A. The first thing that you're always going to do when evaluating a limit is literally just plug it in. So the first thing that we're going to do is we're going to plug in 3 to the function. So go ahead and do that and see what you get. Okay, after some calculation, you should get 0 over 0. So hopefully you remember that this is a very special fraction. 0 over 0 is what's known as indeterminate form. So if we remember that word indeterminate form, it means that it's undecided. We don't know for sure if the limit is going to exist or not, so we need to investigate it. And we don't have a calculator this time, so we're going to have to be a little bit more creative. I want you to think about some things that you could do to this function to change it without really changing it. So see if you can think about what are some ways that I can change the function without fundamentally changing what the function is. So after thinking about this, I see that the top is a quadratic. And my math brain, when I see a quadratic, I think to myself, I probably can factor it. So what I'm going to do is I'm going to rewrite this limit, but this time it's going to be factored. So this is going to be the limit as x approaches 3 of, well, the top is going to factor to x minus 3 times x minus 4. And that's because negative 3 times negative 4 is 12. And negative 3 plus negative 4 is negative 7. So that's how that factors there. All divided by x minus 3. So you might see something interesting here. Notice here how this x minus 3 and this x minus 3 cancel. Technically, graphically speaking, that's what's called a hole, right? So if we end up canceling out a factor in the top and bottom, we would say that there is a hole at x is equal to 3. Okay, so it's basically the exact same graph, we just have a hole there. So if I were to graph this, and I know we're going on into the other example here. If I were to graph this is some sort of quadratic that opens up, maybe like this or something like this. I don't know. They're basically saying that at 1, 2, 3, there is a hole. So I still want to find the limit. What's the limit as x approaches 3? Well, graphically, a limit means what is the y value as I approach the left? And what is the y value as I approach from the right? Well, notice here how these two arrows are pointing to the exact same spot. The hole actually does not affect the limit, and so a limit will exist. And let me show you how we're going to find it. We cancel out x minus 3, and so the new limit that we're going to take here is going to be the limit as x approaches 3 of just what's left over, which is x minus 4. Using direct substitution, I'm going to plug in 3 for x, and subtract from 4, which gives me negative 1. So maybe my picture is not great. It should be shifted down a little bit. But that is the solution here to this first limit. So I want you to use the same process for letter B. I want you to pause the video and see if you guys can find the limit for letter B. Okay, so taking a look at letter B, the first thing you're going to do here is you're going to factor x squared plus x minus 2, which factors to x minus 1 times x plus 2. Notice here how x minus 1 will cancel in the top and the bottom. There's technically what's called a hole there, leaving us with just x plus 2. Plug the limit in by direct substitution for your last step, and you're going to get 1 plus 2, which is 3. And thus, the limit for letter B must be 3. All right, so let's keep moving. Let's try another example. Now, this next example is really the same thing. We're just going to have to do a little bit more work. We have the limit of this huge polynomial fraction expression. I guess it's a rational expression. And we want to know what the limit is. Well, remember the first thing that we always do when evaluating limits is just plug in. So the first thing I'm going to do is I'm going to do direct substitution. So go ahead and plug in 1 and see what you get. Okay, so using direct substitution, we get 0 over 0, which once again we remember is a very special form. It's called indeterminate form. And it implies that the limit might exist. We just need to work a little bit harder to prove it. So in this case here, I would love if x minus 1 were to cancel. So we're actually going to go down memory lane and we're going to try to use something called synthetic or polynomial long division to solve this. And here's how we're going to do it. First thing I'm going to do is, it would be awesome if x minus 1 would work. So the first thing I'm going to do is I'm just going to assume, and this assumption might not be right, but I would love if it was right. Let's assume that x minus 1 is a factor. So if I can assume that x minus 1 is a factor, that means x minus 1 is going to cancel, which is what we want. So using this assumption that x minus 1 is a factor, I'm going to use long division, and I'm going to use synthetic because I think it's going to be quicker. And really quick reminder here, if x minus 1 is a factor, then x minus 1 equals 0, which means x is equal to 1. So the 0 here would be 1. And then I'm just going to put the coefficients of my denominator in. So the coefficients of my denominator are going to be 1, negative 1, positive 1, negative 1. And we're going to use synthetic division here to see what will we get if we actually divide x minus 1 into x cubed minus x squared plus x minus 1. So let's see. Synthetic division says every time I move down, I just add. 1 plus nothing is 1. 1 times 1, though, is 1. Negative 1 plus 1 is 0. 1 times 0 is 0. 1 plus 0 is 1. And 1 times 1 is 1, 0. So our new expression is going to be this. I know for sure that we have the assumption, which is x minus 1 is a factor. So x minus 1 for sure goes in. And what's left are going to be the coefficients here, here, and here. It used to be cubed. Now it's going to be squared. So it used to be cubed. Now it's squared. So we're going to say that this is 1x squared plus 0x plus 1, which would be the exact same thing as me saying x minus 1 times x squared plus x. So what I'm going to do is I'm going to rewrite the limit. The limit is now going to be the limit as x approaches 1 of x minus 1 over my newly factored form. So x cubed minus x squared, this whole thing, factors to x minus 1 times x squared plus x. Well, using what I know here, x minus 1 and x minus 1 are going to cancel. And so the new limit that I get to take is going to be x minus 1, the limit as x approaches 1 of 1, right? Because the same thing divided by the same thing is 1, over what's left in the denominator, which is x squared plus x. And then all we're going to do is use direct substitution. We're going to end up getting 1 squared plus 1 all over 1. And so the official answer here to this limit is a half. Okay, so what I want you guys to do is pause the video and I want you to try letter D using the exact same method. So go ahead and try that. Okay, real quick, I just saw a little mistake I made here. This should be plus 1 here. Thankfully, it doesn't really change our answer. But that right there is actually 1. So still same answer. But there you go. Okay, so taking a look here, I got to this step. We have, we used direct substitution. We determined it was indeterminate form. We assumed x minus 7 was a factor. And then from there, we rewrote the expression after using long division. So we have x minus 7 all over x minus 7 times x squared plus 7, which cancels. So the new limit's going to be a lot easier to take. The new limit is going to be the limit as x approaches 7 of 1 over, well, this cancels, so just x squared plus 7. And so we're going to go ahead and plug that in using direct substitution. This is equal to 1 over 7 squared plus 7, which is 1 over 49, 49, plus 7, which is 1 over 56. So 1 over 56 is the solution here, and that is the answer to the limit. Okay, so let's go ahead and take a look at another example. All right, so the next technique we're going to talk about, so we just talked about the factoring technique. The next technique we're going to talk about is called the rationalizing technique. Rationalizing always has to do with square roots. That's why it's called rational. Think about like a rational expression is one, a radical expression is, you know what, I guess I take that back. Rationalizing has to do with fractions, but in this case, we're going to be dealing with square roots. All right, so what I want to talk about here is the first thing we're going to do for letter A is we're just going to plug in 0 and see what happens. If we plug 0 in, we get the square root of 0 plus 1 minus 1 all over 0. So we get indeterminate form. So we need to find another way to write this expression. And I would say the best way to figure this example out is to use what's called a conjugate. So typically speaking, we're going to be using conjugates when the thing that's causing us problems has to do with the square root. So notice how there's a square root here, there's a square root here. I would love if that square root were to go away because it's causing me a little bit of issues. So what we're going to do is we're going to multiply the top and bottom by what's called the conjugate. So let's go ahead and do that. To multiply the top and bottom by the conjugate, well, the conjugate is going to be this exact same expression. We're just going to change the operation in the middle. So this is going to be the square root of x plus 1 instead of minus 1, all over the square root of x plus 1 plus 1. Okay, so let's go ahead and see how this new limit's going to play out. So now our new limit is going to be the limit as x approaches 0 of, we're going to have the square root of x plus 1 minus 1 times the square root of x plus 1 plus 1 all over x times the square root of x plus 1 plus 1. So I'm going to give you guys some hints here. In general, you are not going to multiply out the non-conjugate side. So in this case, the numerator is the conjugate side, not the denominator, because the numerator is the one that we're multiplying by the conjugate. The denominator, x, is not the conjugate of square root of x plus 1. So as a general rule of thumb, in fact, I'll even type it out here, is the only one that you're going to expand is going to be the conjugate. So do not expand the non-conjugate. I don't know if that's a great way of saying things. Conjugate. Yeah, do not expand the non-conjugate, aka only expand the conjugate. And so what that means is you only want to expand the two expressions that are pretty much mirrors of each other. So only expand the conjugate. Okay. All right, so let's go ahead and expand. I'm not going to expand the denominator, and that's not always going to be the case. Sometimes the conjugate will be the denominator, but in this case, I'm not going to expand the denominator because the denominator doesn't have two pairs of conjugates. The numerator does. So we're going to do this. The square root of x plus 1 times the square root of x plus 1. Well, those are both square root expressions. If I multiply the same square root expression by itself, that would be the square root of x plus 1 squared, and so the square root will cancel. And so this is just going to be x plus 1. All right, let's try the next piece. The square root of x plus 1 times 1 is just going to be the square root of x plus 1. Next one, so we're just using FOIL method. Negative 1 times the square root of x plus 1 is negative square root of x plus 1. And last one, negative 1 times 1 is just going to be negative 1. And this is all going to be kept over the same denominator, which is x times the square root of x plus 1. Once again, we are not expanding the denominator. And you'll see why. Well, notice how these middle terms are going to cancel here. We have square root of x plus 1, negative square root of x plus 1. And also notice here that negative 1 and 1 are also going to cancel. And so this is really nice. Here's my new limit. The limit as x approaches 0 of x plus nothing all over x times the square root of x plus 1 plus 1. So this is really good news. Notice here how these x's are going to cancel. And so the brand new limit that we're going to take is going to be this. The limit as x approaches 0 of 1 all over the square root of x plus 1 plus 1. Well, that's really good news because that x in the denominator was causing me to have a 0 in the denominator, which made it undefined. I'm going to use direct substitution, see what I get. I'm going to get 1 over the square root of 1 plus 1 plus 1. And so my answer here is actually 1 over the square root of 2 plus 1. And we're actually just going to leave it as that. Okay? So I want you to use the same process to try letter B. Okay, so looking here, the first thing we're going to do is multiply by the conjugate listed in red. And from there, we're just going to multiply out just the conjugate part. We're going to leave the denominator, which is not a conjugate, alone. So notice here how we get to this step and we're just left with x in the top. There's an x in the bottom also that's separated by multiplication, and thus we can cancel. That's going to leave me with 1 over 1 plus the square root of 1 minus x, which if I plug 0 into, I get 1 over, you know what, actually, that's not right. I get 1 over, 1 divide by 1 plus the square root of 1, which is 2. So actually, I just get 2. And that right there is the solution. That is the limit. All right, so let's keep going. Next one, we're going to talk about special limits. So these ones require you to use your calculator, which we are pretty familiar with. So what I want you to do, I'm going to walk through the first one with you. We're going to use our calculator to find the limit as x approaches 0 of sine of x. So we can either use the graphing feature, or we can just use the table feature. So what I'm going to do is I'm going to do sine of x. So sine of x, oops, not tangent, sine of x divided by x. And we can graph it and see what it looks like. All right, so if I graph this, I'm looking for what's the limit as x approaches 0. So I'm going to zoom in just a little bit. And we're going to look, what is the limit as x approaches 0? Well, you literally could just scroll and kind of approximate. It looks like y is going to be really close to 1. And that's probably what it's going to be. In fact, we can double check on the table. So if I go to the table here, we have an error. But it looks like I'm slowly getting closer and closer to 1. I can actually change my table set if I want to make sure we stay at 0. Let's change it to 0.1 and just really make sure here. So if I change this, here's what we're going to get. 0.999 on one side, 0.999 on the other side. So yes, the limit is going to be 1 in this case. All right, so go ahead and use the same process to find the limit as x approaches 0 of 1 minus cosine of x over x. Okay, so taking a look at the table, you should have gotten something that was getting close to 0 on both the left and the right. We could have probably been getting like 0.001 and then negative 0.001 or something along those lines. So the answer here would be 0. Okay, so those are the special limits. You are going to have these in your memory. So these ones are just like memorized ones. There's just 2 of them, so no big deal. But these are the ones that you're going to have to memorize. All right, one-sided limits. All right, so this is where limits get slightly more tricky, because to find a one-sided limit, it's not quite as easy as just using algebra. So what a one-sided limit means is this. So if we were to graph this situation here, in fact, I actually might just graph it on our calculator. So let's do that real quick. If I want to graph this situation here, I have the absolute value, which is found in math, number, ABS, of 2x divided by x. So I'm going to go ahead and graph that, and I'll put that on the screen for y'all. Okay. All right, so what we get here is kind of a strange looking function. It's a piecewise function, and it has this big, jump in the graph right around 0, which makes sense, seeing as how if I plug 0 in, I'm going to get 0 over 0. So taking a look at this graph here, it says, what's the limit as x approaches 0 from the positive? What that is saying is, what is the limit as x approaches 0 coming from the right? So when we see this word, the positive, what it means is coming from the right. So coming from the right. So we can see, okay, so what is the height, or what is the arrow approaching as I come from the right? Well, this height looks like it is 2. And so the answer here is 2, and that's using a calculator. But the question is, how do I do this without a calculator? Well, to do this without using a calculator, you're going to have to come up with a number that's pretty close to 0 from the right. Maybe a number pretty close to 0 might be like 0.1. So let's see what would happen if I plug in a number that's pretty close. And this is just going to be an approximation method. So this is the approximation method. We're going to plug in a number really close from the right, like 0.1. So what we're going to get is we're going to get the absolute value of 2 times 0.1 all over 0.1, which we can see pretty easily is going to be 2. And if we try to plug in a number that's even closer, so a number that might be even closer might be like 0.001. If I do that, I'm going to get the absolute value of 0.001 all over 0.001. You can kind of see where this is going. No matter what number I plug in, I'm still going to get 2. And so the limit from the right is 2. But believe it or not, the limit, if we change this for a minute, if I change this limit to be the limit from the left, see how the arrow coming from the left is very different. It's pointing to a very different number. In fact, that number is -2. So just be aware of that. All right, so I want you to use the same method. Go ahead and find the limit as x approaches -3 of the following. Okay, well, taking a look at the graph, we can see for sure there's a jump in the graph. We want to know what's the limit as x approaches 3 from the negative. That means coming from the left, what's the height that I'm approaching? I think that height looks like it's probably, I think it's -1 there. But we can double check for sure using the approximation method. So the approximation method is going to say, let's pick a number that's close from the left. Maybe like 2.9. That's pretty close. So I'm going to do the absolute value. Let's change my color a little bit here. Let's do the absolute value of 2.9 minus 3 all over 2.9 minus 3. Okay, well, the absolute value here is going to make this the absolute value of -0.1, which is just going to make it positive 0.1, all over -0.1, which we can see is going to be 1. If I change my approximation to be even better, like 2.99, then my approximation will be 2.99 minus 3 all over 2.99 minus 3, which is 0.01 over -0.01, which is still 1. And so the limit here must be 1. Okay. All right, let's keep going. All right, so limits from calculus. So this is our last section here. This is the limits that we're going to be using a ton once we actually get into calculus next year. And it's going to be more, maybe a little bit more difficult, but I think you guys are up for the challenge here. So here's a classic limit you're going to see in calculus. We're not going to talk about why we see this. We'll talk about this another time, but this is a classic limit you're going to see. So what we're going to do first is I'm going to tell you what f of x is. We're going to say that f of x is equal to, we'll say it's equal to x squared. So we're going to say f of x is equal to x squared. So the very first thing that I want to do with this limit is I want to establish, okay, if f of x is x squared, what would f of x plus h be? Well, this is just a composite function. What I'm going to do is I'm going to take the red function, right? So this is like a function within a function. I'm going to take the red function, and instead of writing x squared, I'm going to say parentheses squared. Inside the parentheses, I'm going to put my inside function, which is x plus h. Okay, so I know that f of x is going to be x squared, f of x plus h is going to be x plus h squared. And I'm going to plug that into the limit. So here's my limit. The new limit is going to be the limit as x approaches, not x, sorry. The limit as h approaches 0 of my blue function, which is going to be x plus h quantity squared, minus my red function, which is f of x, which is x squared, all over h. And so all you need to do, and this is the goal of all of these problems, your goal here is you want to cancel h. And the reason you want to cancel h is if you don't cancel h, you're going to have a 0 in the denominator when you plug in. So all we're going to do is we're going to expand until we can cancel h. First thing I'm going to do is expand x plus h quantity squared. That is a perfect square trinomial, which means that it's automatically going to FOIL to this. X squared plus 2xh plus h squared, right? So it's, if I had a plus b squared, it's always a squared plus 2ab plus b squared. And then we'll say minus x squared all over h. And so our goal is, let's see what we can cancel. Notice here how x squared and negative x squared canceled, and so now we're left with 2xh plus h squared. Both of these contain an h term, so I'm going to factor 1 out. So if I factor 1 out, what's left on the inside is going to be 2x plus h all over h, and this is the limit as h approaches 0. We're going to cancel the h's here, and so then we just need to use direct substitution. We're going to plug 0 in for h. So 2x remains untouched, that's not h, but h is 0. So 2x plus 0, and so the answer here must be 2x. So let's go ahead and try the next one. The next one's going to be a little bit more challenging, but I think you guys could do it. So the next one I want you to try, and here's what we're going to assume first. So in order to do this, you got to assume some things. Is I want you to first assume that f of x is equal to, in this case, let's say it's equal to x squared plus x. So what you're going to first have to do is you're going to have to establish what would, oh, so I should write this in blue. My bad. Oh, no, that's fine. No, I'm good. Okay. What you next need to do is you need to figure out what is f of x plus h, and that's going to be it by using that composite notation. So go ahead and pause the video, see if you guys can find the answer to this. Okay, so the first thing that we're going to do here is we are going to find the composite function f of x plus h. To do that, we're going to take f of x, and every time we see x, we're going to replace with parentheses. So instead of saying x squared plus x, I'm going to say parentheses squared plus parentheses. And inside the parentheses, I'm going to put x plus h. Okay, so inside the parentheses, I'm going to put x plus h. All right, so then what I'm going to do is I'm going to replace my limit. My new limit is going to be the limit as x, I keep saying x, the limit as h approaches 0 of, okay, we're going to do the blue function first. My blue function is f of x plus h, which is x plus h, quantity squared, plus x plus h, minus, we want to say minus f of x. I'm actually going to put this in parentheses here because the minus is going to distribute to all of f of x. So I'm going to say minus x squared plus x, okay? And this is going to be all over h. And so now our only goal here is to cancel until h cancels. So if we go ahead and use distributive property here, these are both negatives. So this is the limit as h approaches 0 of x. Let's actually distribute that out. This is going to be x squared plus 2xh plus h squared plus x plus h minus x squared minus x. So that was just using distributive property all over h. And so what's going to cancel here is the x right here, the x right here, the x squared here, and the x squared here. Okay? Okay, so with some simplifying here, we're going to get that the limit is 2x plus 1, which is really similar to the last one. All right, I think that is it for today. Some key takeaways, if you want to write them down, would be the first thing you need to do for a limit is plug it in first. Second would be 0 over 0 is indeterminate form, that there's a chance the limit exists. And lastly, if there's a number over 0, the limit is just not going to exist. It either doesn't exist, it's infinity, or negative infinity. All right, so if you have any questions, feel free to send me an email, and you can get working on your website.